Hi grade 10s, good to be with you again. This is Learn Extra and we're dealing with chemistry today. Our topic is chemical calculations. Now, some of you might be thinking, oh, that sounds difficult. Well, it's not really that difficult. It's quite straightforward. We're going to be introducing you to an idea of how you can predict, you can calculate what amount of product will be formed from any reaction. In fact, you'll be able to calculate how much stuff you'll need. And you'll even be able to tell, if I tell you that you've got 10 grams of a certain element reacting with 12 grams of another element, how many atoms there are in each of those samples. So we're into the business of counting and making sure we've got all those ideas sorted out. Now, we'll be basing our session today on some previous knowledge, the understanding of what an atom is and how it's made up of protons and neutrons, how we can use that as a basis for working out the mass of stuff. A unit, we're needing some way of defining the amount of matter, and we've got a way of doing that. So let's have a look at exactly what we're going to do today. We're dealing with chemical calculations, and there are some important principles that we need to understand. And the first one that we're going to start dealing with is the idea of finding the mass of an atom or atomic mass and introducing this concept called the mole. It's a measure of amount of stuff. It's a unit we use to measure substance. It's an SI unit and we're going to be using it a lot. So make sure you've got the story. It's not about furry creatures, it's about a measuring quantity, and it's linked to both the mass of a certain number of atoms as well as a number of atoms. So we'll have a way of working with that. It's also linked to volume, and we're going to remind ourselves about volume of gases just now. Then we're going to say to ourselves, well, let's use these ideas on the mole to talk about composition of substances and ways that we express what goes into different substances. We're going to do some calculation on the amount of substances, and here's a big word, stoichiometric calculations. Now, stoichiometry is simply the idea of applying the conservation of mass, the law of conservation of mass, and using the idea of a balanced equation to do some chemical calculations. Right, so stay tuned, get onto your seats, get a pen and paper ready. You're going to need a periodic table to refer to, so if you've got one, that's great. Make sure it's out in front of you. Let's get going, and we'll start to talk about the idea of atomic mass. Well, the first thing that I need you to understand is that the mass of an atom is mainly contained in the nucleus. So every atom has a nucleus, and inside the nucleus there are protons and there are neutrons. And what we recognize is the electron that's sitting on the outside there doesn't have much mass. We've referred in the past to atomic mass units. So we've referred to atomic mass units. And we've said one proton has an atomic mass unit equal to one atomic mass unit, 1 U. And the mass of one neutron is equal to 1 U. So that means that we've got atomic mass units, and we can base the atomic mass of any atom, different type of atom for different elements, on atomic mass units. So for example, we recognized previously that carbon is made up of many different isotopes, and we could do an average calculation to get what we call the relative atomic mass of carbon, based on the atomic mass units. The one isotope that's most popular is carbon number 12. It's easily separated. We can get it very easily. Carbon 12 will have atomic mass units of 12. Carbon 14 will have atomic mass units of 14. Remember, the idea of an isotope means that they have the same number of protons, same protons, but different number of neutrons. And so, for example, we had carbon 12 and carbon 14. Both of them have 6 protons. They have an atomic number of 6, but this one has 6 neutrons, whereas this one has 6 protons, carbon-14 has 6 protons, but it has extra neutrons. It has 8 neutrons. So when we find the average, and we know that most of carbon is found as carbon-12, when we find the average of the isotopes, the average of all isotopes, we get what we called the relative atomic mass, which is recorded on the periodic table for us. So we can go to any periodic table and we can look for the relative atomic mass. Say, we can think about this relative atomic mass as the average of all the isotopes. But why is it called relative? And that's a really interesting question. We recognize that the mass of one single atom is far too small to put on a scale. We can't measure it. So we've got to measure a big number of atoms. And so scientists through the years, chemists through the years, have chosen different things to compare and try to get a measuring unit to compare. And they finally decided, well, at one stage they thought, well, let's use oxygen as the isotope we're going to look at. And they chose a particular isotope of oxygen and they compared everything else in its mass to oxygen. People decided that that wasn't too easy because we were dealing with gases and it's quite difficult to deal with gases and separating isotopes of gases. So they went to dealing with carbon. So that's one of the reasons why I started with carbon. And so what I'm going to say to you is we have a standard measuring unit, a standard measure, a standard mass. And the standard mass is going to be carbon-12. We're going to say carbon-12, the isotope carbon-12. If we can get a sample of carbon-12, we can compare that to all other samples of any element. So what do? What's our usual way of measuring? Well, our standard way of measuring is using kilograms and grams and so on. So people decided, well, in chemistry, not interested in kilograms so much as grams. So they decided, well, let's take a sample of 12 grams of carbon-12. Now, I don't think it was because of the 12s that they chose it as a standard. It was just easy to do. And they said, well, we'll use this as the measuring tool. So you can imagine now, and do a thought experiment with me. If we use this as a balance, we can then put carbon-12, a sample of carbon-12, certain number of atoms of carbon-12, 12 grams of them. And we're going to say we want to use exactly the same number of atoms of a different element. Well, then we'll be able to measure them relative to each other. Now, using the atomic masses that we did earlier, the scale that we've introduced here, based on the number of protons and the number of neutrons, we'd be able to say that, for example, if we took some hydrogen, a sample of hydrogen atoms. Notice I'm saying hydrogen atoms here, and I want to get the same number. How much mass will I need to get the same number of hydrogen atoms in 12 grams of carbon-12? I want to know to get the same number. I want to put them on the scale. The one is going to be 12 times heavier than the other because hydrogen has only got one proton. So we know the relative atomic mass from the periodic table from our early discussion. The atomic mass units for hydrogen atom is 1. Carbon is 12. So it makes sense that if I need to have 1/12 of the mass, 1/12 of the mass will give me the same number of atoms. 1/12 of 12 grams, well, that's just going to be very straightforward, 1 gram. So if I have 1 gram of hydrogen atoms and 12 grams of carbon-12, then I'm going to say that the important thing is that these have the same number. I have the same number of atoms. And it seemed that this was a good way of doing things. But we need to give a name to this special number of atoms, this special mass of carbon-12. Okay? And so what do we call it? We want a way of measuring stuff we're going to compare everything to 12 grams of carbon-12. Well, we'll say 12 grams of carbon-12 is called 1 mole. So 12 grams of carbon-12 is going to be called 1 mole. And therefore, we'd be able to say that 1 gram of hydrogen atoms is also going to be 1 mole. Same number. But what is that number? Well, that was a really interesting thing, and we'll come on to that in a short little while. Because there were a lot of calculations and a lot of people were doing things to try and calculate exactly how many it is. Maybe you'd like to hazard a guess. How many do you think it is? It's certainly not 12. 12 would be a dozen. This word mole can be thought of as a collective noun, like a dozen represents 12. And we can use it just in the same way. It's not a gross either. A gross is a special name for 144. It's an old-fashioned name, but you can still see it sometimes if you go to a very large supermarket or warehouse and you buy little 5-cent sweets that some shop dealers do. They'll buy packets of them and they'll say 1 gross, 2 gross of sweets in a big packet, suckers or small little sucky sweets. So the mole is much bigger than that. It's not a dozen, it's not 144, it's not even a million. It's hundreds of million, even thousands of million. And the man that first did some investigation into this whole idea around number and the number of particles that we're going to get in this unit of 1 mole, his name was Avogadro. And he was an Italian physicist. His work wasn't very well recognized. He was competing against other physicists at the time, and sometimes they got more recognition than he did. And Avogadro today is remembered because he's given this special number, the number of atoms or the number of anything that makes up 1 mole. And so the number, that special number for 1 mole is given this very special number. It's 6,022. And now we use scientific notation because it's very big. And even on this screen, I wouldn't be able to fit in all the zeros. Times 10 to the 23. And as I said to you, this could be atoms, or it could be molecules, or it could be grains of sand, or it could be the number of stars in the sky, and that's roughly how many it is. If you were to get out into the countryside and you were able to see on a very clear night in the middle of the Karoo, where there's no other scattering of light, and you'd see this blaze of light across the sky, particularly if the moon wasn't up, you'd be able to see hundreds and hundreds of thousands of millions of billions of stars. Approximately the number is about a mole. It's a huge, huge number. If you think about how much sand there is on the beaches of South Africa, if we took 1 grain of sand, we had to count them, we would be able to cover Gauteng, the province of Gauteng, up to the size of a 10 or 20-story building, I think it's about 12-story building, above the ground. That's how much sand we would need, and it would be only 1 mole of little sand grains. Amazing. It's a very, very huge number. But we're going to say that number of atoms is crammed into 1 gram of hydrogen. It's crammed into 12 grams of carbon. Now, that's the basis of what we're going to be dealing with. We're going to have to set up relationships between number, mass, and even we'll see later on volume. Right, now we've been dealing with atoms, and we've been dealing with, remember, every element. When we're dealing with elements, we've got this idea of relative atomic mass. Relative atomic mass. The relative atomic mass is recorded, 1 mole is recorded on the periodic table. So if I want to know the mass of 1 mole of any substance, all I've got to do is I've got to go to the periodic table. Let's go and have a look at the periodic table and have a look here. So, for example, on this periodic table, which is one that they give the grade 12 learners in their final exam, we wanted to know, you'll see the scale is put over here. The bottom number is the approximate relative atomic mass, where the number at the top refers to the atomic number being the number of protons. So 7 grams of lithium, 7 grams of lithium would be 1 mole of lithium. 63,5 grams of copper is 1 mole of copper. Let's do another one. 32 grams of sulfur, over here, 32 grams of sulfur is 1 mole of sulfur. Now, that's fine for dealing with elements. But we know that elements don't just stay on their own. Elements combined with each other to form compounds. So how are we going to calculate the mass of 1 mole of anything? Well, we give it a special name, and this is how we do it. We are going to say, we call this mass of 1 mole the molar mass. The mass of 1 mole of anything is called the molar mass. The mass of 1 mole of a substance is called the molar mass. It has a symbol N, and it has got special units called grams per mole, written like that, G dot M to the minus 1. G dot mole to the minus 1 at least. So let's do one example just as an idea so you can get it. We're going to calculate the molar mass of a substance like sulfur dioxide. So the molar mass, I always put it in a capital M, sulfur dioxide, SO2, close the brackets, and we're now going to use the periodic table to calculate in the right ratio. So let's use the periodic table. Sulfur, notice 32. Oxygen, while I'm at it, just to pick it up, oxygen over there, 16. That's 1 oxygen. So if we have to do it here, sulfur now, 32, there's only one of them, plus 16, but there were 2 oxygens, so times 2. So that gives me 32 plus 32 is going to give me 64 grams per mole. So that's telling me if I have 64 grams of sulfur dioxide, I've got 1 mole. I've got 6,022 times 10 to the 23 molecules of sulfur dioxide. Really important that we've got that sorted out. Now, the one thing that I need you to be aware of, and sometimes it's a trick question, for this calculation, these calculations at least, you need to remember what the diatomic elements are. The diatomic elements are those that occur in pairs. So we can't just use the periodic table and use those relative atomic masses. When we look at something like that is diatomic, like the molar mass of hydrogen gas, we look on the periodic table, you'll notice, as I mentioned earlier, the relative atomic mass of hydrogen is 1, but notice for hydrogen gas, we've got 2 atoms for every 1 molecule of hydrogen gas. So we're going to say the molar mass of hydrogen is 1 times 2, which is going to be 2 grams per mole. Now, that brings us to an interesting idea. Whenever you're looking at something, you've got to decide, have I got atoms, have I got molecules, or have I got something else? I could even have ions, I could have protons. All of these calculations can be done dependent on what you're given. Okay, let's move on and let's make sure that we've got this sorted out. The next section that we want to do, or the next idea that we want to put across, is the idea on molar volume. We're going to say that sometimes we deal with gases, and 1 mole of any gas, doesn't matter what the gas is, occupies 22,4 decimeters cubed at standard temperature and pressure. What do we mean by standard temperature? The standard temperature in this case is going to be 0 degrees Celsius, and that's the temperature, standard temperature. The standard pressure is going to be 101,3 kilopascals. 1 atmosphere, 101,3 kilopascals. So there we've got our standard units. So we've got this relationship that this standard volume of 1 mole of anything will occupy 22,4 decimeters cubed. So now what I've introduced to you is 3 ideas. I've introduced to you the idea that 1 mole can be a number, 1 mole can be a mass, 1 mole can be a volume. So let's just write those down so that we've got them very clear. 1 mole of anything can be the relative or the molar mass. The molar mass, M. Now, 1 mole could also be Avogadro's number. The symbol for Avogadro's number is N subscript A, capital A. Just make sure that you've got the word the word number spelled correctly there. So let's just rewrite it so you can see it. Lumber. I hope that's clear. My writing isn't always that clear. 1 mole of a gas, must be a gas, has a special volume. It's called the molar volume. And we give the symbol Vm to it. Right. Now, if we know what 1 mole is, we've got this relationship between 1 mole being a mass, 1 mole being a number, 1 mole being a particular volume. Is there a way of relating number of moles? Because we're not always going to be given that special number. Sometimes we're going to be given double the number or half the number or some integer value of that number. So how are we going to work out the relationship? There are 3 equations that you need to know and you need to be able to use together. And we're going to practice using them shortly. So what we will say here, the number of moles of anything, the number of moles, is given a symbol. If we're going to write an equation, it's given a symbol N. The mass of a sample, of the given sample, is going to be little m. The number of a sample of atoms, molecules, particles, could be anything, of a sample is going to be called capital N. Okay? And then the volume of a sample is going to be V, capital V. So we're going to take these symbols and try to put a relationship together. We know that 1 mole is equal to the molar mass. So what do you think 2 moles is going to be? That's the number of moles. I'm wanting the number of moles. Number of moles is going to be, let's do it. Let's make sure that we've got it. The number of moles, N. If I'm given a mass, it's going to be the mass of the sample divided by the molar mass. The number of moles is equal to the number of things I've been given divided by Avogadro's number. And the number of moles present of gas is going to be the volume of the sample divided by the molar volume. These 3 equations are the only 3 equations you're going to need. Now, the question is, how are we going to use them? Let's make sure that we've got this right, because it's not difficult to see. If we're wanting to find the molar mass, where are we going to look? We're going to look on the periodic table. So it's not difficult. We've always know at least one. We're going to have to be given another one. Well, Avogadro's number, well, we know that that is 6,022 times 10 to the 23. Sometimes we even round that off to 6,02. The molar volume at STP, 22,4 decimeters cubed. So we can use these numbers and these equations to do our chemical calculations. Let's go and try a couple and make sure that we've got these sorted out. So we'll start off with a really straightforward one, and it says to us, how many atoms are there in 0,5 moles of sodium? Now, immediately, we need to recognize what have we been given. We've been given an element. Elements are made up of atoms. It's not a compound. Elements are made up of atoms. So we're okay. We've got it. We've got it clear. We asked for atoms and we've got atoms. 0,5 moles. Well, now we know that 1 mole of anything is going to be 6,022 times 10 to the 23. So if we only got half a mole, 0,5 mole, then it's going to be half times that number. Well, that's going to be 3,011 times 10 to the 23. Now, we need to make sure that we say that is atoms of sodium. How could we set that out differently? I've just set it out as a ratio. Well, we could use our equation. Remember what we said. We want to find the number of moles. The number of moles is equal to the number in the sample divided by the number of Avogadro's number. So what do we know? We know the number of moles. We know the number of moles. We've got that, N. So we know N. That's N. We know Avogadro's number. That's Na. So if we want to find the number of anything, we can substitute in. Say 0,5 is equal to N divided by 6,022 times 10 to the 23. And then having substituted in, I can then rearrange the subject of the formula and say, therefore, the number of atoms of sodium atoms is equal to 0,5 times 6,022 times 10 to the 23. And you get exactly the same answer as I got earlier, 3,011 times 10 to the 23 atoms. Right, let's go and see if we can do a second one, just to see what sort of things they can throw us and see what they're asking for. Second one is a little bit more tricky. It says, how many atoms are there in 18 grams of carbon? So they haven't given us number. They've given us mass. They've given us a mass. Well, the first thing I'm going to do in most problems like this is I'm going to say, how many moles have I got? So if I can convert to moles, I can always get number of atoms. So where are we going to get the relationship with moles and mass? The number of moles is equal to the mass divided by the molar mass. Remember, molar mass is on the periodic table. But you should remember as well, we said that carbon is the standard. And the molar mass of carbon is 12. If you check it out on the periodic table, there it is. It's rounded off for us, and it's number 12. We've got it clearly over there. So let's substitute some values in and see how we do here. We've got the mass of the sample is 18 divided by 12, and that gives me 1,5 mole. So I now know that I've got 1,5 moles of carbon. I've got 1,5 moles. How many atoms have I got? Remember, carbon is an element. It consists of atoms. So we can still work with that. It's not a problem. We're going to say now we want the number of atoms. Number of atoms is equal to the number of moles times Avogadro's number. And in this case, we're going to say the number of moles is 1,5 times 6,022 times 10 to the 23. Now, just in case you're battling with scientific notation, let's do this on the calculator. And we're going to say, what we're going to do here is we're going to say 1,5 times 1,5 times 6,022 exponent 23. And that gives me an answer of 9,033 times 10 to the 23. So you can read it off from the calculator very easily. Let's write it down. 9,033 times 10 to the 23 atoms of carbon. Okay, let's move to the next one. here we're given another scenario. We're asked about the number of atoms present in a particular volume, a volume of helium gas. Now, you need to remember that helium is a noble gas that just consists of atoms. So we don't have any tricks at this stage. I'll show you some tricks just now. So what we're going to do is we're going to work out the number of moles first of all. The number of moles of helium. Now just one thing, when you get more difficult problems, and it's not a bad thing just to start off right from the beginning, I always like to say what I'm dealing with, the number of moles of helium. And I'm putting in brackets the helium so that people can see that I'm calculating the number of moles of helium. It's going to be the volume of helium present divided by the molar volume. The volume was 11,22 and the molar volume was 22,4. Now, if you do that using a calculator or even in your head, you'll be able to see that gives you half a mole. So we've got half a mole of helium. So the number of atoms of helium is going to be the number of moles times Avogadro's number. And we've done this calculation already. Notice it's the same. Every time we've got half a mole, it's going to be half times 6,022 times 10 to the 23, which is going to give you 3,011 times 10 to the 23 atoms of helium. Right, now we've done the elements and we've done examples with elements. I hope you can see how we're using the different equations to solve our problems. Well, let's see. The next one I think has got a little bit more for us. It's not just dealing with an element now, it's dealing with a compound. But remember, the principle is exactly the same. We're going to work using our three formula together. Here we go. Question, how many atoms are there in 4 grams of magnesium oxide? Well, the first thing I'm going to do, ask myself, what have I been given? I've been given a mass. If I'm given a mass, I must use the mass ratio. So I'm going to say number of moles, which is what I want to find, and in this case, I'm going to be specific. I want to know how many moles of this stuff I've got, of magnesium oxide. Number of moles of magnesium oxide is going to be equal to the mass divided by the molar mass of magnesium oxide. Before I can substitute into there, I need to work out the molar mass of magnesium oxide. Where am I going to go to? Go to the periodic table. Remember, it's got all the relative atomic masses. We can add those together when we're dealing with compounds to give us the molar mass. That's what we want to do. So periodic table, here we go. We're calling it up. Find magnesium. There it is, 24. Find oxygen, 16. We've done that previously. Let's go back and let's add it in. So magnesium is 24. There was only one of them, plus one oxygen, which was 16. So that gives me a molar mass of 40 grams per mole. Now, that wasn't what I wanted. I wanted to know what the number of moles were, first of all, because I'm going to find the number of moles, and then I'm going to ask how many atoms there are. So let's have a look at it. I'm going to substitute into this equation. I've got 4 grams in my given sample, and I've got 40 is the molar mass, and that turns out to be 0,1 moles. So it's not too difficult to recognize if I want to find the number. Now here becomes the issue. I want to find the number of these particles. Magnesium oxide. It's an ionic compound, so I'm going to do the whole and treat it as if it was a molecule, MgO. I want to find the whole number, and I'm going to say I've got 0,1 moles of this. How many molecules or particles have I got, or units of Mg and O? Mg and O, I'm going to say it's the number of moles times Avogadro's number. 0,1 times 6,022 times 10 to the 23, and that's going to give me 6,022 times 10 to the 22 particles of MgO. Now, guys, here's the trick. I've been dealing with MgO. The question asked me for atoms. Now, I need to recognize in this molecule or this substance, I've got an equal number of magnesium and oxygen. Together, I've counted the pairs. I've counted the number of pairs of magnesium and oxygen. So how many, if I know the number of pairs, how many are there going to be in all? Well, from this calculation, I hope you can see that if I know that there are that number of magnesium and oxygen pairs, then I'm going to have 6,022 times 10 to the 22 atoms of magnesium and 6,022 times 10 to the 22 atoms of oxygen. So I can say I've got double the number. In other words, I'm going to add these two together, and that will give me 1,244 times 10 to the 22. Still times 10 to the 22. It hasn't increased. So I beg your pardon. It's 1,22 times 10 to the 23. I did increase it because it added up. So it's 1,22 times 10 to the 23 atoms. And this includes magnesium and oxygen atoms. There is another way of thinking about this. When I went back to the original, let me show you exactly where I'm at. I worked out that I've got 0,1 moles of magnesium oxide of that. Now, if I know that I've got 0,1 mole of magnesium oxide, I could at this point say, therefore I know that I've got 0,1 mole of magnesium and I've got 0,1 mole of oxygen. So that means I've got a total of 0,2 moles of atoms. And if I know that I've got 0,2 moles of atoms, then I can say the number of atoms is equal to the number of moles times Avogadro's number. And if you do this calculation, 0,2 times 10 times 6,022 times 10 to the 23, you'll get the same answer. Let's just check it. 0.2 times 6.022 exponent 23 equals 1,2044 times 10 to the 23. And I think you'll see that I made a slight error in calculation the first time, but it does make sense that I've got it right now. So let's write it down and make sure that we've got it right this time. 1,2044 times 10 to the 23. And that's the number of atoms in total. Just correct this one. Remember when I added here, I missed out the 0, and I just see that now. So I'm going to put the 0 in there, and we've got the right answer. They've confirmed it. You need to understand, though, that our thinking needs to be very clear when we're dealing with compounds and number of things. We need to ask ourselves what's happening inside. Okay, so let's make sure that we've got that one all sorted, and we're on to the next one. Now, instead of asking about the number of things, we're now going to ask about how many moles. And in a way, this is a little easier. We're given the mass, and we're asked to find the mass of chlorine gas. Now, the first thing, as soon as I see chlorine gas, I'm going to write down the formula for it, Cl2. So if I know a mass and I want moles, I'm going to say the number of moles is equal to the mass divided by molar mass. I'm going to use the periodic table. Molar mass of chlorine gas is going to be 35,5. This one's rounded off. Some periodic tables give it a 35,45, but we'll work with this one, 35,5, but it's times 2. And if we multiply by 2, then what you're going to see here is that this turns out to be 71 grams per mole. Okay, and what mass were we given? Well, we were given 70,99. Well, 70,9 divided by 71,0, I think you can see it's going to be close to 1 mole. Let's check it. 70,9 divided by 71, it's going to be very close to 1 mole. It's 0,99. We normally wrote to 2 decimal places. The 8 is above 5, so we round it off. So you can see that that rounds off to 2 decimal places, 1,00 mole. Okay, I hope you're getting the idea. We're using the 3 equations to establish the relationship. We're reading the question carefully and making sure we've got the calculation sorted out. This set of questions, we're asking about the mass of substances. Let's see what we're given in the next one. We're told in the next question that we are given 1,8 times 10 to the 24 molecules of CO2. Now, if we're given that number of molecules of CO2, let's do some calculations about the number of moles. First of all, number of moles is equal to, we've given a number here. So it's the number divided by Avogadro's number. The number was 1,8 times 10 to the 24 divided by 6,022 times 10 to the 23. So if we substitute this in, we substitute this into our calculator, let's see exactly what we're going to get. We're looking for the number of moles, 1,8, and 1,8 was multiplied by 10 to the 24. Exponent 24 divided by 6,022 exponent 23. This will give me the number of moles. And again, in this case, I'm going to write it down as 2,98. I round it off to 2 decimal places. The last unit over here was a 9. Make that 2,99. So there we go. We've got the number of moles as being 2,99 moles. And that's exactly what we were required to do. We're given that number of molecules. This is moles of CO2 molecules. Be very careful that you've got an understanding of what we're asking. So we've got it right. How many moles are there in that number of molecules? It's almost 3 moles of molecules. But now let's have a little sidetrack just for a minute. Recognize that that means that we've also got how many moles of carbon? Well, if I have 1 mole in 1 molecule, I've got 1 atom of carbon, and in 1 molecule I've got 2 atoms of oxygen. Then that means that in 2,99 moles of CO2, I've got 2,99 moles of carbon. I've also got twice the number, 2,99 times 2 moles of oxygen. And so you can see how this ratio works out. It's really important that you can recognize the ratios that are involved. Let's do one more problem, and then we're going to go to a short break. So here we're given the question about the volume. We're given volume of methane, and we're told that the volume is the volume of the sample, 5,6 decimeters cubed. So what's the number of moles? Number of moles, volume divided by the molar volume, 5,6 divided by 22,4. And if you do this on the calculator, you'll be able to work it out quite quickly. 5,6 divided by 22,4 gives us 1/4. So we know that it is 0,25 moles. Now we can write it as moles in full. Normally we should write the abbreviation. I just wanted to write it so that you're aware. This is 0,25 moles of methane. Now please be very careful. When you give your final answer, it should be to MOL, the abbreviation, which is the standard unit. Okay, I think it's time to go to a short break. After that, we'll get into some more problems. Welcome back, grade 10s. I hope you're staying with me. This is an important section, but I hope you can see that if you get the basics of those three equations sorted out, you can find the moles in anything. If you're given volume, you can work out the number of moles. If you're given the number of molecules or number of atoms, you can calculate number of moles. If you're given the mass, you can calculate number of moles. This is really important. There is one last system that you're going to need to deal with, and that's what happens in a solution. We've dealt with chemistry in solutions, and there's a way of defining how much stuff is dissolved. We call this the concentration. Now we could talk about the grams of solute dissolved in the solution, but it's more preferable. The SI units for concentration talks about the number of moles of solute. Remember solute, the solid stuff that gets dissolved in the volume of solution, not the solvent, because when we make up a solution, we're going to dissolve stuff in and then measure the volume of the final solution. It's more fair that way. So when we talk about molar concentration, this is what we're saying. Molar concentration is a way of measuring the amount of stuff dissolved. It's equal to the moles of solute that is dissolved in a given volume of solution. It's measured in mole per decimeter cubed. Now the relationship, we can write an equation for that. We're going to say concentration is equal to the number of moles divided by volume, or we can change it around and say the number of moles is equal to concentration times volume, and that's there. Now what's important here is the units of volume are in decimeters cubed. And we often get problems where we're asked to convert. Let's go and have a look at one like this so we can calculate the number of moles. It says to us, we want to find the number of moles. How many moles are there in a 25 centimeter solution of 2,5 moles per decimeter cubed of HCl? So what have we been given? We've been given the volume, and we've been given the concentration. Remember what I've just said? That if we want to work out the number of moles is equal to the concentration times the volume. But we must make sure that it's in decimeters cubed. So concentration was 2,5 times, now centimeters cubed to decimeters cubed. We must change it. The volume is given as 25 centimeters cubed. To get it to decimeters cubed, you divide by 1,000. So we're going to say 25 times 10 to the minus 3 decimeters cubed. Now that's just a shortcut of dividing by 1,000, and it's quite elegant to do it that way. So 25 times 10 to the minus 3. Let's put it on the calculator and see what we get. And there we go, 2,5 times 25 divided by 1,000, or multiplied by minus 3, 10 to the minus 3, and we push the answer and it tells us that it's 1/16. In decimal terms, that's 0,0625. 0,0625. 0,0625 mole. Okay, now that concentration calculation is really quite important so that you've got a clear sense of when we're dealing with solutions, and lots of chemistry takes place in solutions, as we're going to see just now. Now, one of the other useful tools of this idea or concept of a mole is to see what things are made up of. And so there's a section that we deal with composition, and there are three important formulae or terms that you're going to need to know. Let's just go and have a look at those. The first one is percentage composition. This gives a ratio of elements present as percentages. So for example, I could be given different samples of compounds. So you could get iron oxide and you could get iron 3 oxide. They are different percentages of iron and oxygen. And what we'll be able to do using some techniques in the laboratory is to work out the percentage of iron in each calculation, and then from there be able to work out the formula. So we can use percentage composition to know how much stuff there is in ratio to each other. The second term that we've used and you need to know about is empirical formula. Empirical formula is the simplest whole number. It's not a percentage, whole number ratio. So in terms of the iron oxide there, it might be a different percentage by mass, but the ratio would be 1 to 1. Or in the second case, the ratio is 2 to 3. It's a simple whole number ratio. Notice it's been cancelled down. Now, the molecular formula is what the molecule actually consists of. It's the exact number of atoms in the molecule. So particularly when we're dealing with organic compounds, they might have an empirical formula that you can't really make a molecule from. But the molecular formula tells you you've got so many carbons and so many hydrogens. It gives you the exact relationship. Right, now we can do some calculations to calculate both empirical formula, percentage composition, and molecular formula. Let's go and have a look at a couple of those. So the first one says calculate the percentage of each element contributes to the overall mass of chlorobenzene. We've been given the formula. The formula is C6H5Cl. The first thing we're going to do is say, let's work out the formula mass, the molar mass, and it's the molar mass of C6H5Cl. Now, how are we going to do it? We're going to work using the periodic table. We know that carbon is 12, 12 times 6, plus 1 times 5, and then plus, if you look back on the periodic table, we've done it already. For chlorine, we're looking at 35,5. And we'll just add that in. We've got 1 chlorine, which means we've got 35,5 over there. Now, when you add these together, which equals 112,5, and the units are grams per mole. Now we're going to use this value to work out the percentage of carbon. What we're going to say is, let's take the percentage of carbon by saying the contribution that carbon makes divided by the total. So we're going to take this value here and divide by the total, and so we'll write it in over here. 12 times 6 is going to give us 72 divided by 112,5, and we want that as a percentage. I'm not going to do that in my head. I'm going to use the calculator. So there's the 112,5. I want to say 72 divided by 112,5 multiplied by 100 over 1, which gives me 64%. So write that in, 64%. Next, the next part of the
molecule that we want to look at is the contribution that hydrogen makes. So we're going to say the percentage of hydrogen is going to be 1 times 5, which is 5, and it's going to be 5 out of 112,5 multiplied by 100 over 1. And let's work out what that percentage is. Clear the calculator. 5 divided by 112,5 times 100 equals 4,44%. So we're going to write that down. 4,44%. And the last contributor is the chlorine. So we want to get the total here. We're going to take how many chlorine molecules did we have? Well, we had 1 chlorine atom, only 1 chlorine atom in the molecule. So let's work the percentage out. We're going to say the percentage of chlorine contributes to the mass of the molecule, 35,5 divided by 12,55 multiplied by 100 over 1, and that on the calculator gives us multiplied by 100, which equals 31,56%. Now, if you add these up, you will see that they add up to 100%, and so that you know that you've got the correct percentage composition of this particular molecule. Okay, that's how we do calculations of percentage composition. Find the total mass first, the contribution of each one to the total, and we've got it sorted out. Right, next one now gives us the percentage composition and asks us to find the empirical formula. Look at this. It says we've got a chlorofluorocarbon, which is one of the gases that contributes to the depletion of the ozone layer. A particular CFC is 58% chlorine, 31,543% fluorine, and 9% carbon. Now, what's important here, it's the percentage by mass. We can't just put a simple ratio together and hope that we're going to get a number. What we've really got to do here is say a percentage gives us a sample mass of 100. Let's pretend we've got a 100-gram sample. Then what we're saying is in that 100-gram sample that we've got the chlorine is going to make up 58,64 grams, and the fluorine is 31,43 grams, and the carbon is only 9,93 grams. So what I'm going to say is I'm going to use the masses, the percentages as masses. I'm going to say the mass that I have in 100 grams of chlorine is equal to 58,64. Now, if I want to get the ratios of atoms to atoms, because that's what the empirical formula is, the easiest way is to start with a mass and convert to a mole. So that's exactly what I'm going to do. I'm going to say I've got 58,64 grams in a sample of 100. How many moles have I got? So that's the next point. The molar mass of chlorine as an atom is 35,5, and that's grams per mole. And I'm wanting to find the number of moles. The number of moles of chlorine, put it in, what I've got, number of moles of chlorine, is going to be 58,64 divided by 35,5, which is equal to, calculator comes into play again, so let's do it. We've got 58,64 divided by 35,5, and that's equal to 1,651, 1,652. I'm going to round to 3 decimal places. 1,652. That's moles. Remember, it's moles. I haven't got space to put the unit in, but I'll just write it below it. Now, let's do the same for the others. So I'm now going to take the next one, which is fluorine. I'm going to say the mass of fluorine is equal to 31,43 grams. The molar mass of fluorine, look at the periodic table. Fluorine, 19. Okay, so fluorine is 19. And so how many moles of fluorine have I got? Moles of fluorine is equal to the mass of fluorine, 31,43, divided by 19, and the calculator will give me the answer, 31,43 divided by 19 equals 1,654. 1,654. What? 1,654, which is very close to that one. I hope you can see the number of moles seems to be very close there. The last one is the mass of carbon. I was given the mass of carbon to be exactly 9,93. Remember, this is the mass in 100 grams. That's why we've taken the percentage and we've said, let's pretend we've got a 100 gram sample. And we've said, out of that 100 gram, 9 grams, 9,93 grams is going to be carbon. Then the molar mass of carbon is going to be 12. We know that from the periodic table. So the number of moles of carbon present are 9,93 divided by 12. So here we go with the calculator. We're going to say 9,93 divided by 12 gives us an answer of 0,8275. 0,8275. 0,8275 mole. Now, to get the simplest ratio between these numbers, it's not really that difficult. What we're going to do is we're going to take the smallest number, the smallest one of these numbers that we've calculated, and divide that smallest number through by the whole, through all of them. So let me show you what we're going to do. We're going to say, I'm going to just rewrite it over here. Remember, we had chlorine as 1,652. So chlorine was equal to 1,652. Fluorine was equal to 1,654. And we've got carbon is equal to 0,8275. Now, to get the simplest ratio, this is in a ratio 1,6 to 1,6 to 0,8. To get it to the simplest form, what I'm going to do is I'm going to divide all of the numbers by 0,8275. Divide that one by 0,8275. Divide that one by 0,8275. And now I work out a ratio. Well, 0,8275 divided by 0,872 is 1. There's no debate about that. So let's just do the next one, which was the chlorine. We got 1,652 divided by 0,8275, and that's equal to 1,996. 1,996. 1,9, it was 996, 1,996. Let's do the next one just so that we've got it. Even though the numbers are quite close, I want to make sure that we've got it right. 1,654 divided by 0,8275. And we get an answer of 1,9987. Now, if we had to round that off, it would be 1,99. And we could even put another 9 there. make that one a 9,9. So there are two ways of dealing with it now. We could say, this is really close to 2 decimal places. We could round this off to the closest number is to 2 decimal places. It's 2. That one is 2. And that one is clearly 1. So the empirical formula is going to be 1 carbon, and then we're going to have 2 fluorines and 2 chlorines. The ratio is 1 is to 2 is to 2. That's an empirical formula. Now, if you look at it, you'll recognize that that could also be the molecular formula. It's a very simple chlorofluorocarbon. Carbon has 4 bonds, so we can have 2 of those bonds being to fluorine and 2 of them to be chlorine. So it does seem right. If we wanted to be a little bit more pedantic, what would happen if we didn't get it as close to a whole number? Well, we'd have to multiply through by a common factor, a common number like 2, until we get to a whole number. So if you get a number in your empirical formula that, for example, after calculating the number of moles that rounds off to 2,5, then you have to multiply everything by 2. So 2,5 will become 5, and everything else will also double up. Right now, we've covered the composition type questions. What we're going to do now is take a short break. And after that break, we're going to come back and we're going to look at using equations, balanced chemical equations, to find answers using the mole principle. So don't go away. We'll be back straight after this. Welcome back, grade 10s. Right, now we're getting into the last type of problem that will deal with using the mole as a way to do calculations, and these are quite important. So we're going to do just a couple of examples to show you. We refer to them as stoichiometric calculations because they're based on a balanced chemical equation, and you'll see exactly how it works. We're using the same principles as we've done all the way along, just making sure that we've got everything in place and using the idea that when things are in a balanced chemical reaction, there is a fixed ratio between the reactants and the products. So here's the question. It says a 300 centimeters cubed of a 0,1 molar solution of sulfuric acid is added to 200 centimeters cubed of 0,5 molar solution of sodium hydroxide. And the first thing that they're asking us to do is to write down a balanced equation for the reaction which takes place when the solutions are mixed. Okay, so let's do that. We're first going to write down sulfuric acid, H2SO4 is sulfuric acid. Sodium hydroxide is NaOH. When they react together, they're going to produce sodium sulfate. Swap partners. Sodium has a symbol of, or a charge of +1. Sulfate has a charge of -2. That's why we're going to need 2 sodiums for 1 sulfate. It's a salt that is formed plus water, H2O. So you will see that the hydrogen has come from here, and the oxygen and hydrogen has come from there to form the water. Now, we need to make sure that this is balanced. Remember the rules of balancing. We've got to check the number on each side. Where we see an imbalance, we need to correct it. And the first thing that I notice is I've only got 1 sodium here, and I've got 2. So I'm going to correct it, balance, and get them even, put a 2 in front of that one. Now I've got 2 sodiums. I've got 4 hydrogens. I've got 1 sulfate on this side. I've only got 2 hydrogens on that side. I've got 1 oxygen on that side, 2 oxygens on the left-hand side. So if I put a 2 in front of that, then look what happens. I've got 2 oxygens, 2 oxygens, 4 hydrogens, 4 hydrogens, and 1 sulfur, 4 of those oxygens, and it looks to me like it's balanced. What this is saying is, in ratio, I've got 1 quantity of that, or 1 mole of these molecules, will react with 2 moles of these to produce 1 mole of that and 2 moles of water. And that's really important that we recognize from the balanced equation that there is a ratio of moles. It doesn't tell us that we've got 2 moles. We might only have a fraction of those, but they've got to be in that proportion to give us the complete reaction. So let's do the second question. And the second part of the question asks us the following. It says, calculate the number of moles of sulfuric acid which were added to sodium hydroxide. So let's get the original information. And the original information was we have a volume of 300, we have a concentration, and we want to get the number of moles. So I'm going to go down here and I'm going to say the number of moles of sulfuric acid is going to be equal to the concentration times the volume. Now, in this particular case, what I need to recognize is I've been given the volume as 300 centimeters cubed. I'm going to change that to decimeters, divide by 1,000, make it 0.3. Now I can substitute in, and I'm going to substitute in and say the concentration was 0.1 multiplied by 0.3, and if I use the calculator, don't even really need to, but let's do it. 0.1 times 0.3, and that gives me 0.03 moles. So using a tenth, multiplied by 0.1, it means dividing by 10, 0.03 moles. Now remember what I said about the reaction, and this is the part that we've got to do in part C. Is the number of moles of sulfuric acid enough to fully neutralize? That means react completely with the sodium hydroxide solution. Well, the first step over here is I'm going to calculate the number of moles of sodium hydroxide. So let's do that. The number of moles of sodium hydroxide is equal to the concentration times the volume. The volume was given to me as 200 centimeters cubed, which I'm going to rewrite in decimeters cubed as 0.2 decimeters cubed. And I've got the concentration. So the concentration for this particular one was 0.5 moles. It was more concentrated, times 0.2. And if I do that, I'm going to get the following. 0.5 times 0.2 gives me an answer of 0.1. So write it down, 0.1 mole. So now, when we want to answer question C, is the number of moles of sulfuric acid enough? Well, the only way that we can tell is by writing that balanced equation again. Sulfuric acid plus 2 lots of sodium hydroxide will give us sodium sulfate plus 2H2O. Now, the ratio is 1 mole to 2 moles to 1 mole to 2 moles. So what we need ideally is we need the ratio of sodium hydroxide and sulfuric acid to be in the correct ratio. The ratio of sulfuric acid to sodium hydroxide must be 1:2. So what we recognize is that we've only got 0.03 moles of sulfuric acid. That means that how much sodium hydroxide is going to be used up. Now remember, to get from 1 to 2, you simply multiply by 2. The ratio is 1:2. So how many moles of sodium hydroxide are going to be required? Well, I multiply that by 2, and I see I'm only going to use up 0.6 moles. But guys, what have I just calculated? I calculated the amount of sodium hydroxide present was 0,1. That means I'm going to have leftover sodium hydroxide, and that's not good. I'm going to have 0,1 minus 0,06, which is equal to 0,04 moles of sodium hydroxide left over. So to answer my question said, have I got enough sulfuric acid? No, you don't. You need to get more sulfuric acid because you're going to have 0,04 moles of sodium hydroxide left over. The other way of doing it, of course, is you could work backwards. You could say, from that balanced equation, I know that the ratio is 1:2. I know the ratio of them is 1:2. So this was sodium hydroxide. This was the sulfuric acid. And simply, I knew that I had 0,1. So how much of this am I going to need? I'm going to need 0,05. So I haven't got 0,05. Look, I've only got 0,03. So I've got too little. I'm short of 0,02 moles are required. Extra are required. I don't have enough. So either of those two approaches, either working with the sulfuric acid moles or working with the sodium hydroxide moles, you can solve the problem. Now, I hope that helps you to see the power of stoichiometric calculations. But let's do one more, and then I'm going to leave you to do some practice. It says in this example that we've got 96,2 grams of sulfur, an unknown quantity of zinc, and they react according to the reaction. Zn plus S gives us ZnS. So that's a nice straightforward 1:1:1 ratio. What is the mass of zinc you will need for the reaction if all the sulfur is to be used up? So the first step in any one of these sort of reactions or these calculations is we're going to say, well, how many moles have we got? Remember, this is a ratio of moles. So I know that I've got 96,2 grams of sulfur, and I want to work out the moles. So I want to say, what's the number of the moles of sulfur? So the moles of sulfur is equal to the mass divided by the molar mass. The mass is 96,2, and the molar mass was 32. I can check that on the periodic table. We've used it already, but let's just do the calculation for this one. We're going to say 96,2 divided by 32, and that gives me exactly 3 moles. I'm going to round it off to 3 moles. And say, I need 3 moles. 3 mole. Okay? So what I need, the question, I've got 3 moles of sulfur. What I need to know is what the mass of zinc you will require. So I need 3 moles of zinc. What's the mass of zinc? Well, the mass of zinc is equal to the number of moles times the molar mass. The number of moles, remember from the equation, it's a ratio of 1:1. So if I have 3 moles, of sulfur, I'm going to need 3 moles of zinc. So I'm going to multiply this. I'm going to say 3 times the molar mass of zinc. Go to the periodic table quickly and find zinc is 65. There it is. It's swiveling around. Not worry about it. There it is, 65. And we're going to multiply 3 by 65, and we'll get the answer that we require. So we're going to say 3 times 65. That will be the mass of zinc, 195,41 grams. 195,41 grams. Write it in over here. 195,41 grams of zinc is required. Now, the next part says calculate the theoretical yield. Yield is the mass of the product. Well, we know that if we've got 3 moles of reactants, and the ratio is 1:1:1, then we're going to expect 3 moles of zinc sulfide. So 3 moles of zinc sulfide, we want 3 moles of zinc sulfide. So we need 3 moles of zinc sulfide. How are we going to do that? We know the molar mass of zinc. Remember, we're going to get the mass here. The mass is going to be the number of moles times the molar mass. So the number of moles is 3. The molar mass, let's just do it quickly, zinc was 65 plus 32 for the sulfur. It's a simple calculation. Let's put that all onto the calculator and see if we can work that out. We've got 65 plus 32 gives us the molar mass, 97, times 3 gives us the answer of 291 grams. So the amount that theoretically I can produce from the correct amount of zinc, the correct amount of sulfur is 291 grams of zinc sulfide. The last question says to us the following. It says, hey, when we do the reaction, we only get 275. So what was the percentage yield? So how much out of the did we actually get? Well, to get percentage yield tells us that what we do is we get the actual, the mass of the actual, divided by the mass of the theoretical and multiplied as a percentage. And when you do that, you're going to say 275 divided by 291 times 100, and calculator will help us. 291 is the denominator, so we're going to say 275 divided by 291 multiplied by 100 gives us an answer of 94.5%. So it wasn't too bad. It was a good return. 94.5% was what we got. And in anybody's game, that's not too bad. Well, guys, unfortunately, we've come to the end. There are lots of these type of problems, and my suggestion to you is to do as many practice problems as you can, and the more you do, the more confident you will get. I wish you well for this section. From me, John, goodbye.